Our discussion class gatherings begin tomorrow. I remind you again about the importance on your part to attend such, because in the main, the discussion class gatherings will function as an extension of this class. In other words, lecture. I want our discussion instructors to learn how to be teachers. So we give them material to present to you, just as if they were here delivering the lecture. Which means if you don't go to discussion class, you may well miss new material. Also, regarding discussion class, I sent a number of you email messages yesterday. If since yesterday you've not checked your email, please do so that tomorrow you will know the correct discussion class location that you're supposed to go to. Anybody with us today for the first time? If you're with us today for the first time, you've got to be sure you get these syllabi. If you got them, well, fine. If not, come get them right now. Anybody with us today who was not with us on Friday? If you're in that category, you need to come get one of these information sheets. Please get. Regarding the information sheet, I say again, we want you to have this document with you for each class gathering. This is the same document you'll receive a copy of when you take any quiz or exam. It contains a whole lot of information which you will need in dealing with a quiz or exam. I don't expect you to memorize any of this stuff, but I do expect you to be able to use it. And you'll find out that a great deal of what we discuss in class has to do with how to use and understand this information. Now, chemical equilibrium. Again, extremely important consideration, because the equilibrium state is the most stable state, most stable thermodynamic state in which a reaction system can exist. That means practically, under appropriate conditions, all reaction systems will be in equilibrium. And we as chemists, therefore, need to understand this state and know how to deal with it. Because when a system's at equilibrium, it no longer leads to net production of products for the reaction under consideration. So if you have to make a given quantity of products from a given quantity of reactants, and all the reactants you have need to be converted to products, but the reaction you're studying goes to equilibrium after 50% conversion of reactants to products, you've got to know how to overcome that. So a whole lot of what we will discuss and consider, same for laboratory, will involve how to deal with this successfully. How to get this system to react past the 50% conversion condition, the equilibrium condition. How to outfox equilibrium. Just about all of synthetic chemistry and important industrial chemistry is about this. So regarding such, we've talked about, in brief, the equilibrium condition, which is established when, for a reaction system, the rate of the forward reaction and the rate of the reverse reaction for that very same reaction system become equal. How do we write the reaction equation for an equilibrium system? We told you last time about what you need to be able to deal with. To write the reaction equation for an equilibrium system, to write the reaction equation for any chemical reaction. Shorthand reference, PSI. Remember what that stands for? Principal System Inventory. It is absolutely impossible to deal successfully with the chemistry of a system if you don't know what's in the system. I think that's eminently obvious. And I hope you recall, therefore, in Chemistry 2045, we introduced you to this very important consideration, starting with Assignment 4 and carrying on with Assignment 5. Remember doing that? Principal System Inventory. What materials are used to prepare a system? And on preparing the system, do the materials used engage in a reaction? If so, after the system is prepared, the principal system inventory will show that you have materials different from the materials with which you began. If textbooks would simply learn this, they could start to get at this wonderful, important subject called chemistry far more effectively. And that's why I don't use any general chemistry textbook in this gathering, because I haven't yet found a general chemistry textbook which understands this simple consideration. That being, you cannot understand the chemistry of a system if you don't know what the heck's in the system. So with that, we talked about how to write an equilibrium constant expression, and then we left you with these considerations. 4 systems, all of which you studied in Chemistry 2045 laboratory. I hope you remember this, because most of you were in Chemistry 2045 laboratory last term. And you wouldn't be here if you hadn't been grade-wise successful with that course. 1 molar calcium chloride. I got here some calcium chloride, reagent grade, high quality stuff, and some deionized water, about 400 milliliters. Let's take a good slug of calcium chloride. Finely divided crystals. Let's put some more in there. We'll be generous. Now you saw the calcium chloride itself is a white crystalline solid. After 1 or 2 quick shakes, you see any white crystalline solid remaining in here? So I asked the question. Be careful when you answer this question. In this system, a system resulting from dissolving calcium chloride in water, is there calcium chloride in this system? And the answer is no. When will the textbooks learn this? For this they'd write CaCl2aq. There ain't no such a stuff. What the hell's the point of writing a formula which is totally incorrect? Even any textbook will tell you, when you write an equation for a reaction, you include exclusively and only formulas for substances, which in chemistry means a pure substance, element or compound, or a species. What species are we familiar with in chemistry? What species do we deal with on a regular basis in chemistry? There are 3 of them. What are they? Species. Ions. What else? Molecules. What else? The most fundamental. Atoms. That's it. So when you write an equation for a reaction, in this reaction equation, you're either going to have the formula for an element, a compound, an ion, a molecule, or an atom. That's it. There's no other possibilities. There's our system. We see all the calcium chloride which I added, and I added a fair amount, dissolved readily. What chemistry occurred when we prepared the system? Here's the reaction equation. And you folks recognized, and correctly so, and that's good. This reaction destroyed all the calcium chloride which I dissolved by a process known as dissociation. All the calcium chloride decomposed by this process known as dissociation. All ionic compounds, when they dissolve in water, this got nothing to do with how much compound dissolves. The compound which does dissolve dissociates. What's that mean? The equation for the reaction tells you what it means. The ionic compound separates into its component ions. That's all it means. And the component ions for calcium chloride are calcium ion and chloride ion, and we added the tag AQ just to remind you that the solvent is water. Because practically speaking, all the chemistry that we will do or consider in class and that you'll do in laboratory will be in water solution. We already reminded you, hey, there's no question whatsoever that the most important chemistry in this world is chemistry in water solution. That's what we are. We're a water solution chemistry system. Blood, sweat, tears, urine. Hey, these are all extremely important water solution chemical systems. Now let's look at system B. I will not demonstrate system B because you won't see anything, and I'm not going to bother bringing out here a cylinder of hydrogen chloride gas, because hydrogen chloride gas is not a very pleasant material with which to deal. So if I'd let some of the hydrogen chloride gas escape into this atmosphere, we'd all have to get the hell out of the room. And I don't want to do that, because that would cost valuable class time. And I will do anything to prevent loss of valuable class time. But you studied this process in Chemistry 2045 laboratory. Not directly. You didn't make any hydrochloric acid solution. But in assignment 4, you made some conductivity measurements on hydrochloric acid solution. Remember that? A little handheld gadget. Not very fancy, but adequate. And what in the main did you find from your conductivity measurement results? What did you find out? What were you trying to find out about the system whose conductivity was being measured? What were you trying to find out? Why did you make these conductivity measurements? Other than because the guy who wrote the lab book, namely me, told you to do it.
Percent dissociation. How much dissociated?
How much? Well, yeah, you could get at concentration. That's a statement of how much. But how did you get at extent of dissociation? What did you measure?
Ions.
No. You measured conductivity, which is a reflection of what? Not concentration of mobile ions. Yeah. That's what you measured. And if you make conductivity measurements on 1 molar hydrochloric acid solution, you will find out that every hydrogen chloride molecule used to prepare this 1 molar HCl solution is converted to hydronium ion and chloride ion. Now, I don't call this reaction dissociation. You could call it that, but I think a better term is ionization. Why? Because this is a molecule, and this is a molecule. But when these molecules reacted, we made ions, didn't we? So this is an ion-creating process. So I'll call it ionization. I think that's more meaningful than dissociation. Clearly, this is a dissociation process. The HCl molecules dissociated. But more to the point, on dissociation, they reacted with water to create ions. So we'll call this ionization. This is not an ionization process, because calcium chloride itself is ionic. What would you do to prove in the laboratory, if you had the wherewithal to do this investigation? What would you do to prove that calcium chloride is an ionic compound? What would you do to prove that sodium chloride is an ionic compound? What would you do?
Compare electronegativity.
I want to know by experiment in the laboratory, what you would do to prove that a compound is ionic as opposed to molecular.
Heat it up.
Heat it up. And heat it up how hot? Until what? Until the material melted. Then what? Measure conductivity of the molten pure stuff, you betcha. And you will find out it's a marvelous conductor. Hey, you could use molten sodium chloride as the conductivity system in your household. But I don't know what kind of wires you'd have to maintain temperatures above 800 centigrade. That's what you'd have to have. A little bit clumsy. On the other hand, if you melt a material like sugar, which is also a white crystalline solid, because beside being conductive in the molten state, ionic compounds are all crystalline solids under normal lab conditions. They're not liquids, they're not gases. Molecules, on the other hand, molecular compounds can be gases, liquids, or solids, but they can be crystalline solids, like sucrose, common table sugar. But if you melted sucrose, common table sugar, and tried and did a conductivity observation on it, you'd get no conductivity. So you know the stuff you melted in that case was molecular. In any case, if it is true that in preparing this 1 molar HCl solution, all the HCl molecules dissolve, react by this process, convert to ions, the extent of the ionization is how much? How much? In terms of percent, how much? 100%. That means, among other things, I'm in the lab. There's my Van Gogh replication of a stoppered flask in the laboratory. If you'd like a personally autographed copy of this for $20, I'll give it to you. I got to get beer money somehow. There's the label on the bottle. What does the label tell us? Does the label tell us what's in the solution? Absolutely not. What the label tells us is what was done to prepare the solution. The label tells us that for every liter volume, because that's the way molar concentration is defined, for every liter volume of solution, 1 mole of solute HCl was dissolved. That's what that tells us. But what's in the solution, the only way you can know what's in the solution is to know chemistry. And the chemistry that corresponds to this process, the dissolving of HCl, is described by this reaction equation. So if you see this bottle, this flask in the laboratory, and it bears this label, and now you're asked to, for this system, give its PSI, what will you give? What are the main components of this 1 molar HCl system? I'm listening. Water, hydronium ion, chloride ion, and that's it. What do the textbooks write for this system? They write this. When I see this, I get out my red pen, do this, and take off 1,000 points. Because that's dead wrong. What the hell's the point of writing a formula for something which simply and flatly does not exist? It's without point. Now then, back to A and B from an equilibrium standpoint. The calcium chloride which we prepared is contained in this flask. And the task I assigned you regarding these 4 systems is, after considering these systems, does equilibrium exist involving solute? Here's our calcium chloride system. Is there equilibrium existing in this flask, in this solution, which contains solute calcium chloride? No. Yes or no? No. How do you know the answer is no?
It could dissolve.
You don't see any calcium chloride in there, do you? That's right. So no equilibrium in this system involving solute. How about in the HCl solution system? Any equilibrium involving solute? No, because all the HCl molecules reacted. Now let's look at the acetic acid solution. You also studied this in assignment 4 by conductivity. Now, in the laboratory, this is last term, those are the two solutions whose conductivity you observed in assignment 4. What'd you find out about the relative conductivities of these solutions? Now, I'm asking you to tell me if you remember what you got. Two solutions whose conductivities you observed in assignment 4. What'd you find out about the conductivity of this solution?
Very high.
How high? Did you get an on-scale conductivity reading with this solution? No, it was off-scale. The ion concentration of this solution was too great, greater than the readout capacity of the simple meter which you used. You had to dilute this to get an on-scale conductivity reading. What did you find out about conductivity of this solution? Was it on scale? Yes or no? Yes, it was. That tells you not only does this solution contain ions, that's correct, but it contains ions at a far lower concentration than this. Now tell me, if in the 1 molar acetic acid solution, if the acetic acid molecules as solute ionized by this reaction, there's the reaction. If the acetic acid molecules ionized to a reaction extent of 10%, how would the conductivity of those solutions compare? They'd be the same, which means the 1 molar acetic acid solution would have gave you a conductivity reading that was off scale. Did you find that? No. The acetic acid solution conductivity was on scale. That tells you the extent or degree of ionization in the 1 molar acetic acid solution is pretty small, you betcha. In fact, in 1 molar acetic acid solution, these molecules ionize by this reaction to an extent of only 0.4%, less than 1%. And when we tackle acids and bases in Chapter 18 in greater detail, you'll understand how to get that number. This leads us then to a conclusion. In this solution, does equilibrium exist involving solute? Absolutely. Because after this goes 0.4%, this condition is established. These are now aqueous phase. And the equilibrium constant expression is, now let's put it over here. For C, what's K? What's the equilibrium constant expression? There's the equilibrium reaction. Do you remember what to do to write an equilibrium reaction? Pardon me, an equilibrium constant expression? The concentrations or partial pressures of products are referred to in the numerator of the expression. Concentration or partial pressures, if you have gases, are referred to in the denominator of the expression. And even though solids and or solvent may be part of the equilibrium reaction itself, solids, solvent are or are not included in the equilibrium constant expression. Are not. Good. So with that, you can write the equilibrium constant expression for C. Write it on your paper right now. Did you write this? If you wrote anything but this, what you wrote is incorrect. And when we get to chapter 18, we will learn that this equilibrium constant expression has a special name. It's called the acid ionization constant for acetic acid, Ka. Some textbooks refer to this as acid dissociation constant. Again, I prefer the term ionization because C like B is an ion creating process. So I prefer ionization to dissociation. And you'll also find out in chapter 18 that this equilibrium constant can be evaluated for acetic acid in water at a temperature on the order of 25 centigrade. It's 1.8 times 10 to minus 5. You'll find that on the information sheet. You don't have to memorize it. And when we get to chapter 18, we'll show you how that number is found. Now let's go to D. Another system which you prepared and investigated in 2045 laboratory. Here in a second flask, again got about 400 milliliters deionized water. Let me get some paper towels. So I can wipe off my spatula, because I'm now going to reach into the calcium carbonate reagent bottle and snag some calcium carbonate and transfer it to this second flask. I put a fair amount in there, but not as much of the calcium chloride that I used in preparing the calcium chloride solution. We'll stopper this and shake it up. Before we allow the system to settle, are you already able to make a reasonable decision about whether or not in this system equilibrium exists between involving solute?
Yes.
What's the observation?
Yes. No.
What are you seeing? Are you seeing opacity? Is that a fancy word? Do you all know what that means? Now, on standing, you will see that the opacity of the liquid part of the system will clear, because what I have done by shaking is to suspend a bunch of very, very small particles of calcium carbonate in the liquid part of the system. But those particles are more dense than the system itself, than the liquid part of the system, and they'll settle to the bottom. And then we'll see that in this system, unlike the calcium chloride system, in this system we have undissolved solute, don't we? Equilibrium exists involving solute? You're daggone right. Now let's try to write the reaction equation. Calcium carbonate an ionic solid? Is calcium carbonate an ionic solid? What are its component ions? Calcium ion and carbonate ion. You have to be familiar with this fundamental nomenclature. So we could express the reaction which occurred on preparing saturated calcium carbonate solution. We know the solution saturated because after preparing we shook it vigorously and we see a bunch of calcium carbonate settle to the bottom and not dissolve. That's why we know for this system we have an equilibrium. Write the equilibrium constant based on this reaction equation. On your paper right now, write the equilibrium constant for this reaction system. Did you write this? Did you leave out the calcium carbonate? We'll also learn when we get to chapter 19, this equilibrium constant expression also has a special name. Like this is Ka for acetic acid. This one is known as KSP, the solubility product constant for calcium carbonate. You don't need to hurry up, write that down. You'll see this information is on the information sheet. And this equilibrium constant reflects, but is not a direct measure of, the solubility of calcium carbonate in water. Pretty small number, isn't it? Saturated calcium carbonate solution, which we just prepared, has a calcium ion concentration multiplied times a carbonate ion concentration equal to this number. So the concentrations of these ions, since in preparing this solution each came from dissolving this, the concentration of these ions, large or small? Small. Now,
Is this ionization?
no, this is dissociation. This is an ionic compound. It's a dissociation process. Now let's ask a $64 question which relates to chapter 19. You're not responsible for this now, but I like to plant seeds. I like to be able to go to chapter 19 and say, how many of you remember when we talked about this during our third lecture? And everybody who doesn't remember, I take out my rubber band and thwack them. Ha ha ha. That's me, a dirty bastard. I'll do anything to get you to learn this stuff. How do you think the calcium ion concentration and carbonate ion concentration for this solution compare? This is the dirty question. Let's do an investigation. I didn't pre-test this investigation, so maybe it won't work. If it doesn't work, I'll explain why, and then we'll do it again until it works. Ha ha ha. Here's our saturated calcium carbonate solution. Here's a bottle which bears the label phenolphthalein. You familiar with this stuff? What does phenolphthalein do? What's it known as? It's an indicator. What does this stuff indicate? pH. In what fashion? Color. You'll use this, for example, in 2045 laboratory when you did the acetic acid titration part of assignment number 3. Remember that? Because phenolphthalein in a water solution at a pH on the order of 9 or lower is colorless. Is that clear? Clear means transparent to light. It is not a description of color. Strawberry Kool-Aid is clear. It's transparent to light. But it's hardly colorless. But at a pH above 9, this stuff develops a red-pink color. It develops a red-pink color because the phenolphthalein molecule is a large molecule and it's an organic acid. At pHs above 9, this large molecule loses its H+ to a substantial degree. And the species you produce when this stuff loses H+ is red-pink. That's why when you expose this to a solution which is fairly basic, you see red-pink. Let's see if we can see red-pink with our calcium carbonate saturated solution. I hope so. Aha! Red pink? Lipstick pink? I don't know, and I don't care. You see, my wife doesn't use lipstick. And I'm glad, because I don't like the stuff. Now then, this observation has told us that there's something else happening when we made saturated calcium carbonate solution beside this reaction. What's the something else that's happening? Have we not found that this solution is distinctly basic? Oh, that's quite red-pink. Right? The pH is distinctly above 9, which means when calcium carbonate dissolved in water, beside putting calcium ion and carbonate ion in solution, what other species was produced? Hydroxide ion, right? So we've left something out of this chemistry. Now let me ask you another dirty question. What's the formula for hydroxide ion? And here's the chemistry we left out. Beside this reaction occurring, simultaneous with this reaction on preparing the saturated calcium carbonate solution, was the reaction of carbonate ion, which is a Bronsted base. If you look at this information sheet, you'll see that in the acid-base table, in the base column, you'll see the formula for carbonate ion. You don't need to hurry up and look at that now, but if it's convenient, take a peek. And it has the capacity, therefore, to react with water and produce hydroxide ion. And it produced hydroxide ion by snagging H plus from the water molecule. The H plus landed on this to make the hydrogen carbonate ion. Now, in textbooks, you usually see the formula for the hydrogen carbonate ion written like this. I don't like that formula. Because if I use this formula, and I ask you to describe the most important property of this species, the most important property of any species, what is the most important property of a chemical species? Structure! That's why Lewis structures are so important. If I give you this HCO3 minus formula, since you're just learning this stuff, and I ask you using this formula to write the Lewis structure for hydrogen carbonate ion, I'll bet you all will bond H to carbon. And you'll be wrong. Unless you do better. But if I write HOCO2 minus, I'll bet you'll all write this Lewis structure correctly. So I'm not going to do this. I'm going to do that. And how in the hell textbooks could call the hydroxide ion this? I'll never know. This is oxyhydride ion, a non-existent species. It suggests that the negative charge rests on hydrogen. When you tear up the water molecule to make hydroxide ion by breaking either of these HO bonds heterolytically like this, the previously bonding electron pair winds up in the valence environment of the oxygen atom rather than the hydrogen atom. Doesn't that seem reasonable to you? Yeah. Isn't oxygen an atom much more capable at stabilizing electron density than hydrogen? Why so? It's more electronegative. You betcha. Hydroxide ion. I don't know what the hell this is. Now then, with this, We go to, my erasers are here, a demonstration of equilibrium. Let me draw pictures. Now, this demonstration is discussed in the notes. Oh, starting at about page 17. I don't remember in the discussion of this demonstration that's in the notes which flask is A and which flask is B. That doesn't matter. For the demonstration as I have here set it up, not flask, pardon me, but cylinder. These are cylinders. Here's cylinder A. Here's cylinder B. So as we have the demonstration here set up before us, A contains I2 iodine dissolved in water along with potassium iodide. Now, I purposely have the water containing some potassium iodide because iodine, as I'm sure you know, is not very soluble in water. Water is a highly electric polar solvent. I2 is a simple diatomic homonuclear, therefore nonpolar molecule. And because of this property, it's not very soluble in water. So we treat the water, when we want to get additional iodine to dissolve into it, we treat the water with a source of iodide ion, potassium iodide, an ionic compound of K plus and I minus, so that I2 molecules will react with I minus ions to make this an ion, because ions are rather happy in water as a solvent, because water is highly electric like ions. Here's an assignment for you. Determine the hybridization for the central I atom in I3 minus and determine the structure of this ion. But back to the demonstration. In cylinder B, I have the same amount of water. I think 200 milliliters. And the same amount of potassium iodide dissolved within. All right? I2 dissolved in water with potassium iodide, so in the main you're looking at I3 minus, showing you this color. B, water plus potassium iodide. Now we're going to treat these cylinders respectively with the contents of flask A. Treat with 200 milliliters toluene. There's a quasi-Lewis structure for the toluene molecule. Have you seen this construction before? Benzene ring. The toluene molecule is a benzene ring with a methyl group attached to it. Do you think this is particularly polar? You think it's slightly polar? Slightly polar it is. So, do you think it's a fair statement that toluene is certainly a better solvent for I2 than is water? Because of the similarity in their electric natures, their polarities. None for I2, slight for toluene. So, to complete the demonstration, we're going to treat flask cylinder B with 200 milliliters of toluene that contains the same amount of dissolved iodine as we have already dissolved in cylinder A in the water phase. So take note. The contents of cylinder A, which we've just prepared, and the contents of cylinder B, which we are presently preparing, are identical. Each contains 200 milliliters of water. Each contains the same amount of I2. Each contains the same amount of potassium iodide. And each contains the same amount of toluene. Equal volumes for the immiscible liquid phases. Are these systems at equilibrium? Why can we conclude they're not at equilibrium? Compositionally, they're identical. If they were at equilibrium, how would they look? Identical. What can we do to get these systems to be at equilibrium quickly? Shake them up. Why does that get the job done? What we're now doing is magnifying greatly the surface area contact between water and toluene. This gives the opportunity for I2 as solute to exchange between the two phases quite rapidly. Let's see. Just take a few seconds. If what we wind up with will appear to be development of equilibrium in each cylinder, with the equilibrium we've developed being this: I2 aqueous in equilibrium with I2 toluene. In which layer? Notice that toluene is on top of water because toluene is less dense. In which layer is it obvious that most of the I2 is dissolved? The upper toluene layer, which keeps with our conclusions about solubility of I2 in toluene versus I2 in water based on electric nature. We'll pick it up from this point tomorrow in discussion class.